Hello everybody, in this tutorial we will be doing a rigid jointed frame analysis using a finite element software Midas Civil. The objective of this exercise is to compare the results from a finite element software with that of the hand calculations. This example consists of a pitched roof portal frame which is pinned at two supports, support A and support H, and there is a pin connection between the members CD and members DEF at the point D, which is a pin. There are some loads applied on the structure, which include few point loads in the in the lateral horizontal direction, and some vertical loads, point loads, and uniformly distributed load on top of the roof. The objective of this tutorial is to calculate the support reactions at A and H and sketch the axial load, shear force, and the bending moment diagrams. This example is a two-dimensional analysis example, so we will be doing all the modeling in two dimensions or X, Z plane. So let's start. So that's the blank Midas Civil window. I go to File and New Project. Okay, and we'll set up the analysis mode to two dimensions. So we go to Structure, Structure Type, and change it to XZ plane. Okay, then the unit system in which we will be working is kilonewton meters, so we can change the units from the status bar at the bottom of your screen, or you can change it from tools, unit system, kilonewton meters, and apply. And uh, for for making it more clear, we can switch on the viewpoint, which will show us which are the active coordinates systems in which we are working. So view, and we can click on viewpoint here and click OK. That's the viewpoint. I'll click on the front view. This is the plane in which we will be modeling the structure, that is the XZ plane. Okay, now let's get back to the model or the drawing. So we'll start by modeling the columns first. So we'll start from the left side. So in this example, I'll be using the node by node or element by element modeling approach. So first of all, I'll generate a node. So that's node element, create nodes, and generate a node at coordinate 0, 0, 0, apply, and you can see the node is generated. I can display the node number as well from this option, display node numbers, and that's node number 1. The next thing is creating the column. So the column consists of two divisions. You can see 2.5 meters and 2.5 meters each. Why two divisions are required? Because we are going to apply a force at the midpoint of the column, so we need to divide it. So I'll just create the column using this node as a reference. So the feature that we will use is the extrude option, and make sure it's node to line. We'll use the selection tool, select single, and click on this node to select or highlight it. You can check whether the node is selected by looking at the node number in the node selection box. Okay, then we'll type in the distance. So it's in the Z direction. It's 2.5 meters and number of times is 2, and click apply. So that's the column generated. Next we define on the left half of the pitched roof. So that is 4 meters and in the X direction and 2 meters in the Z direction. So for this we select node number 3. Just click on node number 3 using the selection tool, and in the equal distances box we type in 4, 0, 2, and number of times is 1, and press apply. Front view again, so that's the left half of the roof generated. Next we use point number D to generate the right half of the roof. So that's 3 meters. There are two divisions, so 3 meters each. 3 meters, and 2 meters is the total the height from the top of the roof to the base of the roof. So select this node 4 now, and this time we enter 3 in the x direction, and the z we enter -1, and number of times is 2, and click apply. So that's generated. And finally the column on the right side, that is 3 meters 2 times. So I click on this on node number 6, and now instead of using the equal distance, I will show you the unequal distance option. You can also uh, create or extrude a column out of a node using this option. So 2, you can just type in 2 at -3 meters and apply. So the structure is now generated. So I'll close this dialog box. Now for the analysis we need to enter some properties to our elements, all these elements. So we need to enter some material properties and some section properties. So for that we use the properties menu, go to properties, material properties, add, and we can select a type of material, user define or steel. Let's go for steel and select S355, click OK. Similarly we can select the section, add, and let's say we go for an I section, British Standard I section, let's say a universal beam type of section, and click OK. So you can see the section shape now. Okay, now let's define the support conditions. So we go to boundary, define supports, use the selection tool again to highlight the node numbers 1 and node number 8. So you can highlight by creating a window like this. So 2 nodes are selected, and make sure you select dx and dz, because dx and dz represent the pinned support condition, that is restraining both horizontal and vertical displacements. And once you've done that, click apply, and both the supports get applied at node numbers 1 and 8. Okay, now we will define the pin at node number 4, because from the figure we know that the point D is pinned. So what we will do is release the moments at the end of this member CD. That will be equivalent to adding a pin on the structure. So we use the feature called beam end release. Select this option and use the select single feature. Select the member here. So this particular element is selected. Now we need to pin or release the moments at this end of the member. So instead of pinned, that is being both ends pinned, we need to select either pinned fixed or fixed pinned. Now how to know which end has to be pinned or fixed? That can be seen from the local axis. So again I'll go to display, element, and select local axis and click OK. So here you can see the x-axis, the local axis x points from node number 3 to node number 4. So for each element, uh, the the nodes of the element are referred as I and j, as you can see in the beam and release dialog box as well. So I and j are denoted by uh, the nodes from the local axis actually moves from point I to point j. So that means in this case the I node is node number 3 and the j node is node number 4. So we need to release the j node here, node number 4. So we check on fixed pinned, which will make j node as pinned and I is fixed, and then we click apply, and you can see a small yellow dot is generated which determines which defines the beam and release or the pinned connection at node number 4. Okay, now I'll switch the view to the isometric view by clicking on this arrow, and you will find that uh, I'll just save the model. Okay, so you will find that the y-axis, the local y-axis for all the elements are not aligned in the same direction. Now, for the analysis purpose, it doesn't matter if the axes are aligned or not, but for the result interpretation, you might have some troubles interpreting the results, because the results are beam results or the force results are always generated with respect to their local axis. So say for example, if you're checking the bending moment diagram for this frame, then the bending moment diagram is actually the bending about the local y-axis. Okay, so it's the bending about the local y-axis, or you can say my. So for that bending, if we say select, consider these two columns here, then you see um, the y is pointing out of the screen, as you see in this case. So it's pointing towards us, and the y-axis on the right hand column is pointing away from us. So that will give two different sign of the bending moment and these two columns. So you may have confusion while interpreting the results, as in you'll find that both will have say, if they both have hogging moments over here, but in the results they will show that one is sagging and one is hogging, though the result magnitudes will be the same but directions will change. So we need to be careful about that, and the best thing is we can rotate or change this local axis so that it gets aligned with the rest of the structure. So we can judge from by looking at this view that the local axis of only this column is not aligned, so y needs to be changed. So I will use the selection tool to select these two column elements, and then go to node element, change parameters, and use the element local axis option and select change and type in 180 degrees, so that will exactly bring it in the same direction as the local axis of the other elements. Apply, and you see that y is now reversed, and close this. So now the sign of the bending moment will be exactly what you want it to be. Okay, so I'll undisplay the local axis now because we don't need it. So local axis is undisplayed. Switch back to the front view, and here we have the completed structure. You can see from the work tree what all information you have entered. Now the next thing is applying loads on the structure. So we have quite a number of loads on this structure which we need to apply. So just like we did in the previous examples, we need to apply the loads by first defining a load case name. So I'll go to the software again, select load and select static load cases, and give a name. So let's say load case P is the user defined load case, add. Then we'll start assigning some values to this load case name. So we go to nodal loads. Let's see what values need to be defined. So I'll just keep this on a second screen so that I can quickly copy the values. Okay, so we'll start with the horizontal loads first. So we enter 12 kilonewton here, and select the node number 2, apply. Then we select node number 3 and enter 8 kilonewton. Then we select node number 6, enter 5 kilonewton, node number 8, node number 7 and enter 8 kilonewton. Okay, so all the horizontal loads have been applied. Now we'll apply the vertical loads, point loads. So we'll select point 3 and make it 0 and enter in the FZ minus 15, minus because it's in the downward direction. Select node number 4 and change this to 25. Node number 5, change it to 35. And finally node number 6 and changing it to minus 20 and apply. Okay, so all the point loads have been applied. I'll close this. You can right click on the works tree nodal loads to display the values. So that's how it looks like with all the point loads applied. Now we will apply the UDL. So we have a uniformly distributed load of 12 kilonewtons per meter over the member CD. But if you see, it's not along the entire length of CD, but it is applied on the projected length only. So we need to be careful about this when we are applying the loads. So for applying the uniformly distributed loads, we go to loads element and select direction is global Z, vertically downwards. Enter the value as minus 12. Make sure you check on projection because you are applying the load on the projected length of the member. So check on yes in the projection and use the selection tool to just click on the element that you need to load, and once you've selected it you can click on apply and it will apply the UDL or the uniformly distributed load on this member. Now it may seem from the display that it is been applied on the entire structure, but internally the software actually considers only the projected length, so you don't have to worry. No need to worry if the display looks as if it's applied on the entire structure. The software takes into account the projection. Okay, so all the loads have been applied. Now we can analyze the model. So I'll undisplay the loads here and undisplay the node numbers as well to make it more clear, and go to analysis and click on perform analysis. So analysis is done. We can check in the message window there are no warnings or errors, so that means the results can be trusted. So we go to results and let's check the reactions first. Select reactions, check on values, use this small box to enter the number of decimal points you want for the results. Click OK and you will find the reactions displayed on the screen. So these are the reactions. Then we can check the deformation of the structure. So you may you should be careful for the deformation stresses because they depend on the material and the section properties, even for a determinate structure. So though the reaction and forces will be independent of the properties that you enter for a determinate structure, but deformations depend. So we don't need to calculate the deformation for this exercise, but I'm just showing you how you can see it in a finite element software. So we select deformations displacement contour and select DXYZ, check the deformed on and undeformed shape as well. You can turn on the legend and apply. So that is the deformation of this structure. You can see that faded gray line in the background, that is the undeformed shape, the initial shape, and then the final shape. You can make it more realistic by clicking on real deformation. So that makes it more the the displacement to be more curvilinear rather than a straight uh, line type of displacement. So these are the displacements: zero point 0.3 meters or 0.31 meters, that is 300 millimeters approximately, is the deformation of maximum deformation of the frame. Then we move on to forces. We are interested in looking at the beam diagrams, so we select beam diagrams here. We check off the deformation. Let's start with axial force diagram first. So Fx, now for the which component resembles axial force, shear force, or moment, that can be very easily checked from the local axis. So as we saw previously, in the local axis, x represents the longitudinal direction of the element. So any force in that direction, in the longitudinal direction of the element, can be visualized through the Fx. Shear force is calculated for local y and local z, and we are interested in the z direction shear because we are only interested in the forces within this plane. So let me just switch on the local axis, and you can see the z, which is normal to the element. So the shear will be displayed along the Fz, and for the moment we need to see the moment about y-axis of the element, so that is my. So let's start one by one. So for Fx, select exact and select the you can select absolute maximum and apply. So that displays the axial force. If you want to see the forces at either ends of a member, you can also check off absolute max, and you can select I and J and click apply. So that will show you the results at each end of the member. Second thing is the shear force. Apply. So that's the shear force diagram. You can change to solid fill to make it more visible. We can also increase the scale of the diagram, maybe 3 times. Apply, so that it's more magnified, easy to view. Then moments, apply. So that's the bending moment diagram. You can see you have linear variation over here because of concentrated forces only, but over here where you have the uniformly distributed load, you have the variation as curvilinear. So maybe if I increase it 10 times, that's you can see it clearly that it's a curve. Okay, so these are the results that you can obtain from the finite element analysis. Now let's see what results we obtain from hand calculations and what are the differences in the two results. So I'll bring back the document again, and we'll go straight to the hand calculations part. Okay, so for the hand calculations of the statically determinate structure, we first start by calculating the reactions. So we have basically 4 unknowns here, and normally we'll have 3 equations of equilibrium: horizontal forces, vertical forces, and the moment. But because of this spin, we also have a 4th equilibrium equation, which is the moment about this spin. So we can make use of all those equations and calculate these unknowns for the reactions. Once we have calculated the reactions, we split the structure into several small elements and draw the free body diagram for each member. So here we have all the free body diagrams for each member, and for each free body diagram we use the equilibrium equation to calculate the unknown shear forces, axial forces, and the moments. And finally, after doing all these calculations, we come up with these diagrams for axial force, shear force, and bending moment. And you can very easily see that they are exactly same as the results in Midas Civil. So hence we can conclude that the assumptions that we considered for the analysis, they are correct and they match the hand calculations. So the model is done correctly. So this brings us to the end of this presentation, and to know more about the other examples of frame analysis, stay tuned to our YouTube page, Midas UK. That's it. Thank you.